Transverse and longitudinal waves. When a wave advances through the medium, energy gets transferred with the movement of the waves. There are two kinds of mechanical waves: transverse waves, longitudinal waves. Transverse waves, waves in which the particles of the medium vibrate at right angle to the direction of propagation, are called transverse waves. Transverse waves can travel through solids and over the surface of liquids, but not through gas. Waves on surface of water. When a pebble is thrown into a pond of still water, water waves are formed. These waves travel in the form of widening circles with the point of disturbance as the center. If a cork is placed on the water surface, the cork is not carried forward by the wave, but the cork starts moving up and down about its mean position. This implies that while a wave propagates over the surface of water, particles of water vibrate up and down about their mean positions, and the disturbance moves outwards progressively from point to point. The energy given out by the stone to the water at the point where it strikes is transmitted to the other areas of water by the wave. Waves on a stretched string. One end of a long string is tied to a peg on the wall and the other end is held in the hand. A sudden jerk is given. A wave pulse is seen to move along the string. If the free end of the string is moved up and down continuously, a wave is seen to move through the string. Waves move perpendicular to the direction of vibration of the particles of the string. The elevated or raised portions of the string are called crests, C, and depressed or lowered portions are called troughs, T. Crests correspond to the positions of maximum positive displacement and zero particle velocity. Troughs correspond to the positions of maximum negative displacement and zero particle velocity. Longitudinal waves. If the particles of the medium vibrate back and forth in the same direction in which the wave is moving, then the wave is called longitudinal wave. Sound waves are longitudinal waves. When a tuning fork is made to vibrate, sound is produced. The tuning fork's prongs are at rest. Therefore, the layers of air in the surrounding space are equispaced. When a tuning fork is made to vibrate, sound is produced. Strike the tuning fork so that it starts vibrating. When the prong A moves towards right, it compresses the layer of air in contact with it. This creates a region of high pressure called compression. The compressed layer of air tries to get rid of its strain and compresses the next adjacent layer, and so on. Thus, a wave of compression moves towards the right. When the prong A moves towards left, a region of low pressure called rarefaction is produced towards the left. As the prong moves back to the right extreme, it completes one vibration. The number of vibrations produced in 1 second is called the frequency of the tuning fork. Waves on a helical spring. One end of the helical spring is fixed to the wall, and the other end is held in hand. If one end of the spring is suddenly pushed forward, the nearest turns of the spring are compressed. With the passage of time, this compression propagates forward through the spring. If the same end of the spring is suddenly pulled outward, a rarefaction will be seen traveling along the spring. Thus, a longitudinal wave can be produced in a spring by vibrating the spring back and forth. Each turn of the spring makes to and fro movement in the direction of propagation. Displacement of the particles of the medium at an instant for a longitudinal wave traveling towards right is: particles at A, C and E have maximum positive displacement. Particles at B, D and F have maximum negative displacement. Particles from both sides are pushed towards the fixed point. So, they are the centers of compressions. Particles are at their mean positions and have zero displacement. Particles from both sides are moving away from fixed point. So, they are the center of rarefactions. Particles are at their mean positions and have zero displacement. Difference between longitudinal waves and transverse waves. In longitudinal waves, the vibration of particles in the medium is parallel to the direction of propagation of wave. In transverse waves, the vibration of particles in the medium is perpendicular to the direction of propagation of the wave. The longitudinal wave propagates in the form of compressions and rarefactions. The transverse wave propagates in the form of crests and troughs. In longitudinal wave, one compression and one rarefaction constitutes one wave. In transverse wave, one crest and one trough constitutes one wave. Longitudinal wave can propagate in solids, liquids and gases. Transverse wave can propagate only in rigid solids and at the surface of liquids. In longitudinal wave, the pressure and density is maximum at compressions and minimum at rarefactions. In transverse wave, there is no pressure variation.
We have seen how sound propagates through a medium. When the object vibrates, it creates the disturbance in the surrounding medium, and this disturbance is what we call a sound wave. The wave travels in the medium in the form of compressions and rarefactions. But in which direction do the particles of the medium vibrate? Before we answer that question, we will talk about longitudinal waves. What are longitudinal waves? Let me tell you the fancy definition first. Waves in which the particles of a medium vibrate in a direction parallel or anti-parallel to the direction of energy transport are called longitudinal waves. What does that mean? Before we get to the statement, do you remember what parallel and anti-parallel mean? Parallel would be two vectors like this, and anti-parallel will be two vectors like this. Parallel but in opposite direction. Now coming back to the statement, it means that if the wave travels in this direction, then the particles of the medium also move to and fro along this direction only. So the displacement of particles is parallel or anti-parallel to the direction of the propagation of wave. Is sound wave a longitudinal wave? Take this example and try to find out. Yes, sound waves are indeed longitudinal waves. We see this in this example that the particles of the medium are vibrating in the direction of propagation of wave. Sound waves are also called pressure waves. Can you tell me why? It is because the sound wave consists of the repeating pattern of high pressure regions called compressions and low pressure regions called rarefactions through the medium. But wait, hold on. Are there waves in which the displacement of particles of the medium is not in the direction of propagation of the wave? The answer is yes. Let's see one example in which the propagation of the particles is perpendicular to the direction of propagation of the wave. Take a string with one end fixed to the wall. This end is fixed at the wall here, and this one is in your hand. We see a wave when we give the string an upward jerk from this end. What do you notice here? In what direction are the particles of the string moving? Up and down, right? And what about the direction of the propagation of the wave? It's moving to the right. Let me repeat it once. The particles in the string are moving up and down, while the direction of propagation of the wave is towards the right. The particles are vibrating in a direction perpendicular to the direction of the wave. Such waves are called transverse waves. So are sound waves transverse waves? The answer is no, and it's because the particles of the medium are vibrating in the direction of propagation of wave. Here is a quick recap of what we did today. We saw that longitudinal waves are the waves in which particles of the medium vibrate in a direction parallel to the direction of motion. Sound waves are longitudinal waves. Sound propagates through the medium in the form of high pressure and low pressure regions. Hence, sound waves are also called pressure waves. And at the end, we saw what transverse waves mean. They are waves in which particles vibrate at right angles to the direction of its propagation. In the next video, we will understand more about the propagation of sound waves. See you there.